All right, last thing I want to talk about with equilibrium is Le Chatelier's principle. Le Chatelier's principle. And essentially, all this is a principle that says when something happens to a reaction, or rather, in this case, the wording is a system at equilibrium, the direction of the reaction is going to shift to minimize that disturbance. So, what do I mean? Well, there's a couple different things we're going to look at. The first thing I want to look at is concentration. So, what happens if we reach equilibrium and then we change the concentration of a reactant or a product? Well, think about this. If we have something at equilibrium and we increase the reactant concentration, okay, well now we're not at equilibrium anymore, so we're talking about Q here. What we have done, since Q is your products over your reactants, okay, so we've increased the reactant concentration. That means the bottom has gone up. So overall, if the bottom goes up, Q is now going to be less than K. If Q is less than K, to get to equilibrium, it's going to go in the opposite direction. It's going to go toward the products in order to get to equilibrium now. So if you increase the reactant concentration, what's going to happen is Q goes down, so we're going to go toward the products. The opposite happens if you increase the product concentration. So if we increase the product concentration, this is going to go up, which means now Q is greater than K, and to get back to equilibrium where it was, it's going to go backwards. It's going to go to the left, toward reactants. Now, the easiest way to summarize all this is when you have something that disturbs equilibrium, if we increase concentration, wherever you're increasing concentration, it's going to go to the opposite side. So if I increase reactant concentration, it's going to go towards the products. If I increase product concentration, it's going to go toward reactants. If I lower a concentration, it's sort of the opposite. So if I lower product concentration, it has the same mathematical effect as increasing the reactant concentration. So if I lower the product concentration, the equilibrium is going to, or rather the reaction is going to shift toward the products in order to reestablish equilibrium. If I lower the reactant concentration, then it's going to head toward the reactants to reestablish equilibrium. So look at this example. What is the effect of adding carbon dioxide? Well, if I increase carbon dioxide, I'm increasing a product that's going to increase my Q value. So to get back to equilibrium, it's going to go this direction. So what's the effect of adding carbon dioxide? Well, it's going to shift more toward the left side, toward the reactant side. What if we add CaCO3? Well, here's the thing. CaCO3 is a pure solid. It's not even in the K calculation or the Q calculation. So in this case, since we've got two solids, K is merely equal to the concentration of CO2. So is Q. So it only depends on the concentration of carbon dioxide. So this will not affect it whatsoever. The next thing I want to talk about is volume and pressure. So as volume increases, pressure is going to decrease. You get a bigger container and you keep the same amount of gas in there, then since it's a bigger container with the same amount of gas, you have less pressure. However, if you lower the volume, same amount of gas, the pressure is going to go up. If you keep your volume the same but increase the amount of gas, then your pressure is going to go up. If you keep your volume the same and you decrease the amount of gas, the pressure is going to go down. So how do we think equilibrium is going to be affected when we make a change? Well, remember what I was saying about pressure and concentration. Increasing pressure is like increasing concentration. So let's look at this. If you decrease the volume, what's going to happen is you're increasing pressure. This is going to cause the reaction to minimize that disturbance. In other words, it's going to shift to the direction that has the fewer moles of gas, because by going to the side that has the fewer moles of gas, you're actually going to relieve that pressure. If you increase the volume, that's decreasing the pressure. Well, to minimize that disturbance, you're going to shift the reaction in the direction that has more moles of gas so that you can minimize the change in pressure. If a reaction has an equal number of moles of gas on both sides, then changing the volume doesn't have an effect. Also, adding an inert gas, like a noble gas, if you throw that into the mixture, it also has no effect whatsoever. It's only when you are dealing with gases that are within the reaction. So, here, if I decrease the volume of the reaction, so I decrease the volume, that means my pressure is going to go up. So if my pressure is going to go up, I want to relieve that pressure. So the equilibrium is going to shift to the side with the least gas to relieve the pressure. We have 3 moles of gas over here, 0 moles of gas over here. So the reaction is going to shift this direction to relieve that pressure. If I increase the volume, well, now increasing the volume is going to decrease the pressure. To minimize that disturbance, I want to get more gas in there. So the equilibrium is going to shift this way to try to reestablish equilibrium. If I add an inert gas, nothing's going to happen. Last thing is temperature change. Thus far, if we change the concentration or we change the pressure, we have not actually changed the equilibrium constant. We're just changing the things within the reaction. However, if we change the temperature, we are actually changing the equilibrium constant now. So this section is about what happens when we change temperature, and we are actually changing the value of K when this happens. So this all depends on whether it's an endothermic or exothermic reaction. When we have a reaction, plus B, and we got C plus D, and obviously they'll have coefficients, but I don't care about that right now. In an exothermic reaction, exothermic means it produces heat, right? So what you do is you pretend that heat is a product. So in an exothermic reaction, we would add heat over here. So, thinking in terms of concentration, if I increase the temperature of this reaction, which direction is it going to go? Well, if I'm increasing the concentration of heat, that's a product, it's going to shift toward the reactants, like we already talked about. If I decrease the temperature, that's like decreasing the concentration of heat. So in that case, the reaction would shift this way. That's all for an exothermic reaction. In an endothermic reaction, what's going to happen is we have heat to start, right? It uses heat, so it is a reactant. Well, in this case, if I increase the temperature, that's increasing the concentration of a reactant, which means equilibrium is going to shift this way. The opposite is also true. If I decrease the temperature of an endothermic reaction, it's decreasing the concentration. That's like decreasing the concentration of a reactant, so we're going to go this direction. So remember, the fact that it's shifting one way or another is due to the fact that in this case we're changing the value of the equilibrium constant. Okay, hopefully that makes sense. Here is a practice. This is endothermic, okay? Endothermic means it uses heat, so we put heat on the reactant side. If I increase the temperature of the reaction, that's increasing this concentration. So if I increase the concentration of a reactant, it's going to go to the right. If I do the opposite and I decrease the temperature, well, decreasing the concentration of a reactant is actually going to send it this direction instead, so it would go left. This one is exothermic, so that means we're adding heat on the product side. So if I increase this concentration, it's going to go this direction. And then if I decrease the temperature, it's going to go this direction. So hopefully that makes sense. Let me know if you